Well, good evening. Welcome to Space Oddities. Hope you're all well. Thank you for joining us on this Tuesday evening. Good to see everybody again. Who have we got in so far? Let's just say hi to a few people. Gerard, thank you so much for your donation already, sir. Much appreciated. We got Stuart in. Who else? We got people coming in. And Derek's here. Hi, Derek. A few others. Okay. So anyway, we hope you've all had a fantastic week, obviously. And we have. Well, I think everybody here has. And what have we got for you this evening? That's the big question. Well, this evening we're going to be carrying on looking at the future of living and working on the moon, the hazards that astronauts will face when that glorious day happens and people are actually living and working on the moon. So we've looked at gravity, we've looked at radiation, and this week both Dave and Lou will be looking at the rather difficult subject of lunar dust. So you've got that to come. Also this evening, I will be explaining a very famous diagram in astronomy to you, namely the Hertzsprung-Russell diagram, which you may have heard of. Many people think it's really complicated to understand, so I thought I would talk you through it because it's an incredibly important and useful diagram in astronomy. So we'll be looking at that as well. And we've got the usual things. Dave will be giving us another week in. Michael's turn for Constellation of the Week. And unfortunately, there's no Einstein of the Week this week. Sorry about that, but there just hasn't really been anything worth including this week. I think there's just one. So I'll carry that over to next week when I'm sure we'll have more. Okay, before we go any further, if you're new to Space Oddities, you are most welcome. We hope that you'll stay around and consider subscribing to the channel. Guys, can I just ask, please, as always, leave a like on the video, subscribe to the channel if you haven't already, and very importantly, if you could just leave a comment on the video. Those comments are important, otherwise the YouTube algorithm barely notices us. So we'd like to get our viewing figures up, obviously. So please, if when the video appears on YouTube, just leave a little comment if you would be so kind. You can say anything. You can, death threats, ransom demands. We don't care. Anything, as long as we've got a comment in there. So we'd be very grateful if you could do that for us. Don't forget that if you would like to support Space Oddities, you can do so in a number of different ways. The first way is to keep our caffeine levels going by buying us a coffee. And you can either scan the QR code or click the link that's just appeared in the chat, and that will take you to the Buy Me a Coffee page where you can buy some caffeine, and that's much appreciated. Also, don't forget that we have the Space Oddities shop. With summer coming up, everybody in the country will be trying to get hold of these, so get in early to get your Space Oddities t-shirts, £20 including postage and packing. Can't say it fairer than that. And of course, we've still got the hoodies, which you might need in this well, I don't know about you, but we're having a glorious spring. But I bet if you're in the UK, you're not having a glorious spring. So it's probably still a bit chilly. So why don't you buy yourself a Space Oddities hoodie? Is that what you're wearing, Des? No.
Well, no. I'm just saying we're wearing still thermals.
Oh God, really? Yeah.
Not exactly warm up here.
Yeah. Well, we've had, today has been the coldest day we've had all winter. We've not had a colder day. It was so cold today, I actually had to put a coat on to go out. So it was really, really cold. So yes, the hoodies start at £40, including UK postage and packing. And if you're outside the UK, please add total £10 to the total value of your order. Also, if you would like to make a donation directly to Space Oddities, you can do so by clicking the super chat icon. That's the one with the $sign on it immediately under the chat window. And that will allow you to make a donation directly. Your donations are very important to us because it helps us keep the channel going, essentially. And any money that you kindly give us will go towards doing exactly that. And we thank you from the bottom of our hearts for any money you can spare towards helping to keep the channel going. If you like what we do on Space Oddities and we'd like to keep doing it for you, then consider supporting the channel if you can. So that's that. Okay, well, I think we'll move on. And what we'll do now, we'll go straight to this week's news. And let me get this up on the screen. 1 second. There we are. And just get to where I want to be. Okay, so this is the news for the 10th of March 2026. And the first item on the agenda, can anybody identify what's in that image? Anybody see anything like that before?
Wasn't that a fireball? Or was it?
Yeah, it is. It's a spectacular fireball that was seen across much of Western Europe on the 8th of March. And it ended with a remarkably rare outcome. A meteorite fragment crashed through the roof of a house in Cologne, Germany. I'll just give you the reporting of it. At around 1855 local time, observers across France, Belgium, the Netherlands, Luxembourg, Switzerland, and Germany reported a brilliant streak of light crossing the sky. The object, a meteoroid entering Earth's atmosphere at tremendous speed, produced a vivid fireball as friction heated the surrounding air and caused the rock to glow intensely. Thousands of people witnessed the event, and more than 3,000 reports were submitted to the International Meteor Organization. Most of the material burned up completely, but some fragments survived the descent, which obviously slowed dramatically as they descended through the atmosphere. And one of those fragments came down in the Guls district of Koblenz in Germany, where it punched a football-sized hole through the roof of a residential home before landing inside a bedroom. Fortunately, nobody was injured, even though there were people inside it at the time. Initial examinations suggest the recovered fragments are likely chondrites, a common type of stony meteorite that dates back to the early formation of the solar system, about 4.5 billion years ago. Several centimeter-sized pieces were reportedly recovered and will now be studied by scientists. And in fact, that reminds me very much of a daytime fireball that I saw a few years ago when I was just coming out of our local station just as dusk was beginning, and looked up and there was a huge fireball flying through the air. And it was amazing. I was so rooted to the spot I forgot to get my camera out. But you could see the flames. I mean, it was absolutely stunning. And I rushed home to look up whether it had been reported, and it had. I submitted a report to the International Meteor Organization, but it was a lot further away than I thought. In fact, people in Barcelona, I saw it to the south. People in Barcelona, which is an hour south of me, saw it to the south as well. So it was out over the Mediterranean somewhere, where it really ended up. But I've never seen a daytime fireball before, so it was thrilling. But it wouldn't it be great to have a chondrite coming through your roof? That'd be brilliant. I'd give money.
Rito said that's nothing. He nearly got hit by a falling iPhone from a plane near Santa Monica Airport.
No, really?
Yeah.
Dear me.
Okay. That's sort of another thing on roaming charges, isn't it?
Yeah, so we move on now to gravitational waves, which we haven't talked about for a while, but here we are. Well, astronomers have dramatically expanded the known catalogue of gravitational wave events, revealing that the universe is filled with constant ripples in space-time generated by these violent cosmic collisions. As you may know, there are 3 gravitational wave observatories on Earth. The twin LIGO observatories in the United States, Virgo in Europe, and Kagra deep underground in Japan. And they all observe at the same time, so it's really a collaboration. And they've released a new catalogue. The consortium's released a new catalogue, which is known as the Gravitational Wave Transient Catalogue 4.0, or if you're friendly, GWTC4. And it adds 128 new gravitational wave signals detected between May 23 and Jan 24. Now, this roughly doubles the number of known events, bringing the total well beyond the discoveries made during the first 3 observing months. We're on observing 1-4, obviously, at the moment. Most of these signals come from black hole mergers. Other types of signals are much rarer, but that's pretty much what you'd expect. We'll have a look at the actual figures in a moment. So the new detections include 2 mergers between a black hole and a neutron star, as well as systems containing very rapidly spinning black holes. And it also includes the most massive black hole merger yet observed, which we talked about before, involving objects with a combined mass of about 130 times that of the Sun. Some of the signals come from extremely distant events, up to 10 billion light years away, obviously meaning the collisions occurred when the universe was much younger. And if we just have a look at the total number of detections since the first detection in 2015, you see how they break down. Binary black holes, merging black holes, if you like, 300 plus. Binary neutron stars, 2 collisions confirmed, including, of course, the famous GW 170817, which was the first one with an electromagnetic counterpart. That is to say that not only did we detect the neutron stars colliding in gravitational waves, but also in gamma, X-ray, radio, and I think that was about it. And visible light, of course. Neutron star black hole collisions, 3 have been confirmed, and we haven't detected things like supernova, continuous waves and pulsars, or cosmics, the alleged to exist cosmic strings. We're going to need probably the next generation of detectors, including Europe's LISA spacebound gravitational wave observatory, to see those. But this catalogue is growing all the time, and the fact that we've now detected over 300 collisions between black holes just shows you how common they are in the cosmos. Okay, moving on. Well, some good news about UK space. This is Saxonville in Scotland, which is a UK spaceport. The UK government's announced a 500 million investment package aimed at strengthening the country's space industry while supporting both economic growth and national security. And this was unveiled at the Spacecom Expo in London by Liz Lloyd, the UK Minister for the Digital Economy. Makes sense. And represents a shift in how the government plans to prioritize space funding in the coming years. Now, this funding is intended to help British space companies grow and compete internationally while aligning the centre more closely with strategic national priorities. Officials say the investment will concentrate on 4 key areas, expected to deliver both commercial and security benefits. And these 4 areas are satellite communication, in-orbit servicing and manufacturing, space domain awareness, and launch capability. These are seen as high growth markets where the UK could develop a strong leadership. Several national programs will receive funding. So where's this money going? Well, the largest portion, 105 million, will go towards developing technologies for in-orbit servicing, assembly and manufacturing, such as refueling satellites or producing advanced materials in space. The next one is 85 million has been awarded to the National Space Operations Centre, including a new ground-based sensing network to monitor satellites, debris and space weather. Additional investments include 80 million for low Earth orbit, I'll say that again, low Earth orbit connectivity technologies, 65 million for innovation programs, and small allocations for regional space clusters and spaceport infrastructure in Scotland. The announcement forms part of a broader strategy to make Britain a more competitive space power and comes along the UK's 1.7 billion commitment to the European Space Agency. And the UK is going to come up with a wider national space plan later this year, having, of course, closed the UK Space Agency for some weird reason that nobody can quite work out. But there we are. So good news for UK space, another 500 million in investment.
Another bit of good news on there, Andy, if I may.
Yes,
was that we heard the other week the unfortunate demise of Orbex.
Yes.
The satellite rocket launch company. Well, apparently, fingers crossed, Skyora, another UK rocket company, are interested in. Don't know about purchasing the whole lot, but they're definitely interested in acquiring some of the assets and things like that. So
right.
Hopefully, it'll all stay in this country. And I think one of the things is Skyaura, because Orbx were going to launch from the very north tip of Scotland.
Yeah.
Not the one in the Orkneys, but I think Skyaura are looking to launch from there as well now. So
Right, good.
I think
Good.
that's what they're after. So that's some good news. Hopefully things will pick up.
Yeah, because
get things
RFA
moving.
in Germany have their eyes on the Saxavort site.
That's right. Yeah. Yeah.
So hopefully we can, viewers, in case you didn't know, Orbex was a British space company that went bankrupt recently, despite showing much promise and working steadily towards their first launch from Saxavort in Scotland. So it's very sad to see a British company fail like that.
I mean, they were so close. They were so close.
They were so close. Yeah. It's a shame, really. But if Skyaura are going to scoop up their resources and their assets, so that'll
be good. I mean, it just seemed very strange that news came out about Orbex around the same time, well, just after the UK shut down the UK Space Agency. But
I wonder if the two are related in some way.
I mean, remember, we built a satellite launch system and then we scrapped it before we even launched the first satellite, although it did go. But yeah,
wheels within wheels, I think Daz is the answer to that.
Exactly.
Anyway, let's move on. Who remembers DART?
Yep. Oh yeah, yep,
me too.
Would one of our planetary scientists like to give a brief summary to viewers about DART?
Yeah, sure. It was actually a pretty ingenious mission, I thought. They basically had an asteroid with a very, very small companion orbiting it, a very small satellite moon, and they rammed an impactor spacecraft into it at a known velocity, known mass, so they knew exactly what was hitting it, and then measured how much it altered the orbit of the small body around the larger one, in order to try to ascertain for future, if we wanted to deflect an asteroid from hitting the Earth, something like that, how effective that would be, a kinetic impact like that.
Yeah, absolutely. Thank you.
Yeah.
Thank you, Dave. That's great. Believe it or not, that was 4 years ago, 2022. Where does the time go? It's in the news again. Now, don't forget, we've got Europe's spacecraft Hera, which is on its way to observe the aftermath of the impact 4 years ago, and it's going to reach there in December of this year. But the system has been in the news. The bigger asteroid of the two is called Didymos, and the small moon of Didymos is called Dimorphos. So just to tell you which is which. So in this image, we can see the immediate aftermath of that impact of the DART spacecraft ramming itself into Dimorphos. And what they found was that Dimorphos' orbit around Didymos had changed dramatically. Before the collision, it took about 11 hours and 55 minutes for Dimorphos to orbit Didymos. After the impact, it shortened by roughly 32 minutes. So there was a big change in the orbital period of Dimorphos after the impact. NASA were hoping that they could induce a change of at least 73 seconds, and they got 32 minutes. So it was viewed as a huge success. But new research shows the consequences were broader than expected. The collision did not simply alter Dimorphos' orbit within the binary system. It also produced a small but measurable change in the overall motion of the Didymos-Dimorphos system around the sun.
Right.
Wow.
Yeah.
That makes sense, right?
Yeah. The impact blasted large amounts of debris into space, and the recoil from this ejector provided additional thrust that amplified the momentum transferred to the asteroid. Now, this shift in the solar orbit of this binary asteroid system is extremely tiny. It's a minute change in velocity of around 11.7 micrometers per second. But it does represent the first time human activity has measurably altered the path of a celestial body in its orbit around the sun. Now, you may think that a change of 11.7 micrometers per second is tiny, but this is still significant, because what can start off as a tiny change, a tiny initial change, can grow into big effects later. They see this as important proof that kinetic impact missions could someday deflect a dangerous asteroid away from the Earth if detected early enough. And finally, Dimorphos, obviously throwing some sort of hissy fit, now seems to be flinging rocks at Didymos, according to observations, because they found several impact zones on Didymos that appear to be fresh.
Oh, boy.
And there's a little bit, there's quite a bit of uncertainty about exactly how fresh they are, but they've definitely occurred since the impact. And it's thought the impact sort of loosened material on the surface of Dimorphos, which then, because of Dimorphos rotation, got spun off into space and hit Didymos. And don't forget that we found out that Dimorphos is a huge sort of rubble pile, which you could see very clearly in the images before the DART spacecraft impacted. So there we are. So we'll have to wait until December to see what Europe's HERA spacecraft sees in the system, and get some close-up information to see how things have changed since 2022. But an amazing mission,
If only the dinosaurs had been smart enough to pull that off.
Yeah. Yeah.
I mean, it's basically, I mean, if you remember, we covered that live, and that was a real fun night watching that.
Oh, it's great.
Come in. So I know the images were delayed, but to watch it actually zoom past Dimorphos and then heading for Didymos,
that was amazing.
and then it's getting closer and closer and closer, and then all of a sudden it started to produce an image, and then it cut off halfway through as it hit.
That's right.
Amazing,
right.
amazing night.
Yeah, amazing stuff. Okay, where do we go from here? This beautiful image is where we go. Astronomers have produced the largest ever image made by ALMA, which is the Atacama Large Millimeter Submillimeter Array telescope in Chile, which, as you may know, observes in millimeter and submillimeter wavelengths and comprises 66 antennae in a perfect observing spot. So this is revealing the complex structure and chemistry of gas at the very center of the Milky Way. And this focuses on the region known as the central molecular zone, the dense and chaotic environment around Sagittarius A star, our local supermassive black hole. This image is about 650 light years across and shows an intricate network of filaments and clouds made of cold molecular gas, the raw material from which new stars form, of course. Because it's about 27,000 light years away, it's the only galactic nucleus that we can possibly probe in this detail. And this comes from the ALMA CMZ exploration survey. And what they found was both simple compounds and more complex organic molecules, such as methanol, ethanol, and acetone. By assigning different colors to different molecules, the survey reveals how gas moves through the region and gathers into dense clumps where stars may eventually form. Star formation near the Milky Way center occurs under far more extreme conditions than in the galaxy's outer regions. Massive stars form rapidly and often end their lives in powerful supernovae or even hypernovae. By studying the detailed chemistry and structure of the gas in this turbulent environment, astronomers hope to understand how stars are born in the most energetic regions of galaxies. So really what you're looking at, if you like, is the plumbing at the center of the Milky Way. Regions being connected by these filaments of cold gas. And it's a stunning image, isn't it? It's
stunning, yeah, very stunning. Is that a jet to the north or upwards? Do you reckon that's a jet, or is it just
no? It's
the gas sits?
Oh well, no, it's gas. It's definitely gas.
Yeah, I was just going to say more. Yeah, didn't know whether it was being thrown out by the.
No, you're looking at millimeter, submillimeter wavelengths.
Yeah,
so plasma jets wouldn't actually show up in this. So there we are. They're beautiful and really informative image from ALMA looking at the most turbulent region in the galaxy, of course, that being the area around Sagittarius A star. And lastly today, the thing about exoplanets. Now, for decades, we've talked about this many times before, the Goldilocks zone around stars, where temperatures are neither too hot nor too cold for liquid water to exist. And in our own solar system, this extends roughly from Earth's orbit to Mars. And this has long guided the search for exoplanets which could be habitable, because we assume that for life to exist on a planet or even a moon, you need liquid water on the surface. But a new study published in the Astrophysical Journal suggests that this traditional view may be too restrictive. Astrophysicist Amory Wandel argues that habitability should not be treated as a rigid boundary defined solely by distance from a star. Instead, the distribution of heat across a planet's surface and the planet's atmospheric properties may allow liquid water to exist in places previously considered uninhabitable. One key example involves tidally locked planets, which always show the same face to their star. These worlds experience perpetual daylight on one hemisphere and permanent darkness on the other. Earlier models suggested such conditions would make them hostile to life, but the new research indicates that heat from the sunlit side could be transported through the atmosphere to the dark side. In some regions, this redistribution of heat might keep temperatures above the freezing point of water. The study also suggests that liquid water could exist far beyond the outer edge of the traditional habitable zone, hidden beneath thick layers of ice on extremely cold planets. Subsurface lakes or melting beneath ice sheets could provide stable pockets of liquid water, potentially creating environments where life might arise. Now, taken together, these ideas imply that the range of planets capable of hosting liquid water, and therefore possibly life, may be far broader than previously believed. So that's quite interesting, isn't it? Yeah, don't know whether any of that
a bit more. Yeah.
You know, it's funny, if we look at the missions that we're launching to look for life, of course there's Mars, right?
Yeah.
That falls in line with that thinking. But then there is Europa Clipper.
Europa,
not in the habitable zone. Dragonfly to Titan. These are all subsurface ocean scenarios. And then as we look at the Earth, we see extremophiles that can live in all kinds of environments. As well as, what would the Earth be like? What do you think? What would the Earth be like without its significant amount of carbon dioxide and methane?
Colder.
It would be much colder, with probably something approaching what we would call an ice age.
Yeah, definitely.
Oh, I'm invisible. Sorry.
Yes, you are.
Yeah, you are.
We've lost you.
You're coming from the other side. We were channeling you.
Yeah. So, we are being too restrictive on where we're looking for habitable planets. Interesting thoughts. I mean, these are all good thoughts. So we'll have to wait and see. All right then. Let's just have a look in the chat and see who's around.
Yeah, I see Dave put a downside on the DART mission. There we go.
Downer. God.
Right.
I mean, that takes me back to The Expanse, wasn't it? Because that was one of their main refugees.
Yeah, absolutely.
Yeah.
Yes, I mean, theoretically, yes. Whether it will actually, who knows? Who knows?
No. I mean, I don't. He talked about that. I guess Carl Sagan talked about that. It was. I mean, it's definitely. It could work both ways, and but.
Definitely.
It sounds like something Dr. Evil would plan.
That's right.
All world governments hostage, so they paid him
some big bold stroking a cat.
$1 million. Right.
Yes, it's funny Carl Sagan should say that. That doesn't sound like him at all. his normal measured views.
He wasn't. It wasn't. This was a long time ago. I saw this, but it wasn't an argument against doing this. It was
no,
just
I'm sure,
an observation that, it could actually, it could work both ways, which is just interesting.
Yeah,
there was a
knowing
comment
human
there,
nature, isn't it? Yeah, knowing human nature.
Said the man who showed aliens how to get to our planet.
That's right. Yeah. So
Voyager.
it's knowing human nature. We can never. Things we've developed for good can always be turned around and used for evil.
Well, technology is always a double-edged sword, isn't it?
Yeah, right.
Yeah. Okay, say hello to Andy and Dave and Melinda and Di Burrito. How are you, sir? Hope you're well. And Gerard, Joe Delay's here, Anne's here. So you're welcome, guys. Hope you're enjoying the show so far. We're going to go over to our main theme of the evening now, which is carrying on with our examination of the hazards and dangers that future lunar astronauts will face in their efforts to live and work on the moon. So, Deep Rita, thank you very much for your donation, sir. Thank you. What's left of the Artemis budget? Thank you. Thank you very much. Much appreciated. I think we're going to start off with Lou, and then we'll move on to Dave. So I'll let Lou take the floor now. And there you go, Lou.
If someone had told me 20 years ago that my big claim to fame would be talking about dust, I just I would have hoped that would not be the case. But it turns out you can't ignore this. If we're going to have a lunar outpost, dust is the number one concern, apparently, to NASA. And so I could have subtitled this a number of things. It's the little things that mean a lot, or it could be, this whole 100 ways to die in space. I don't know, but it's a problem. So let's take a look at why dust is. It's not that big a problem around your house, is it? Or maybe it is. I shouldn't judge. I'm sorry. But okay, so lunar dust or regolith is considered by NASA to be the number one environmental challenge for lunar exploration. Unlike Earth's dust, which is round and kind of not very jagged because it's been kind of reduced by wind and water erosion, lunar dust is composed of unweathered jagged particles, comparable to kind of shattered glass. And they carry strong electrostatic charge from ultraviolet solar radiation impacting on the surface. So lunar dust is an extremely fine, abrasive, and electrostatically charged powder that covers the moon's surface, acting as a major contaminant for equipment and health. It is characterized by sharp, jagged edges, high adhesion to surfaces, and poor thermal conductivity resulting from constant micrometeoroid impacts in an airless environment. All astronauts who've walked on the moon report difficulties with lunar dust. These problems were likely worsened by the fact that the dust was electrostatically charged, which enhanced its adhesive properties. In order to develop strategies to tackle these issues, it will be necessary to advance our theoretical understanding of the lunar dust plasma environment, as well as characterize its size, structure, composition, and charge. Lunar dust grains are small. They're generally less than 50 to maybe as much as 100 microns in size, but most of them significantly below 20 microns. These grains are highly angular, jagged, glassy, often described as having high stickiness by the astronauts. They are primarily composed of rocky fragments, volcanic ash-like material, and agglutinates, and this is just a fancy word for glassy particles. Due to electrostatic charging from the solar wind and lack of atmospheric moisture, the dust clings strongly to fabric and metal. So the small size, sharp nature, and high reactivity make it capable of causing abrasive damage to equipment and human tissue. We'll talk about this in more detail in just a bit. The dust, which feels and smells like spent gunpowder, that's how the astronauts have reported it, is a major challenge for lunar surface operations. And it necessitates very special cleaning and mitigation technologies. I found a paper by Tim Stubbs, Rich Von Drack, and Dave, I know you know Rich. He used to be head of the Planetary Science Group at Goddard. And Bill Farrell, entitled The Impact of Dust on Lunar Exploration. And I found this in that paper. From the Apollo era, it is known that the dust on the moon can cause serious problems for exploration activities. Such problems include adhering to clothing and equipment, reducing external visibility on landings, and causing difficulty with breathing and vision within the spacecraft. Eugene Cernan, who is the commander of the Apollo 17 mission, stated it this way. He said, "One of the most aggravating, restricting facets of lunar surface exploration is the dust and its adherence to everything, no matter what kind of material, whether it be skin, suit material, metal, no matter what it be, and its restrictive friction-like action to everything it gets on." So that is a problem, dear friends. How are we going to address this? So we mentioned before it's jagged. The sharp edges of the lunar dust particles act like kind of sandblasting jets, especially during landings where rocket plumes kick up high-speed debris. It can kind of eat away at surfaces, scoring metal bearings and tearing through spacesuit fabrics. Why anyone want to go to the moon at this point, I don't know. These fine particles, remember, most of them kind of less than 20 microns, they easily penetrate gaskets, seals, and hatches. And it has historically clogged drills that they brought to the moon, jammed zippers, boy, can that be a problem, and caused rover malfunctions. Dust layers on equipment also absorb sunlight, and so they can cause radiators to overheat because they absorb the sunlight and re-emit in the infrared. It clings electrostatically to camera lenses, solar panels, and helmet visors, significantly reducing visibility and power generation. Dust infiltration accelerates wear on bearings, connectors, and optics, increasing maintenance demands. So hopefully, going back to the moon won't be just a repeat of the ISS, where we send people up to the space station to repair the space station. Hope that doesn't happen. Lunar dust poses significant respiratory, ocular, and dermal, in other words, with your skin, hazards to astronauts due to its abrasive, electrostatic, and fine-grained nature, similar to volcanic ash. Apollo missions revealed it causes lunar hay fever. Surprise. Sneezing, coughing, throat irritation, and eye irritation. Apollo 17's Harrison Schmitt reported sneezing, watery eyes, and a sore throat after dust exposure inside the cabin. Long-term exposure risks include chronic bronchitis, reduced lung function from lung scarring, and in severe cases, cancer from DNA damage. These particles are small enough to penetrate deep into lung tissue, reaching bronchial and alveolar, meaning from alveoli, cells, triggering intense inflammatory cascades. In fact, recent studies show lunar dust simulants kill up to 90% of lung cells in vitro, in other words, in the laboratory, signaling severe potential toxicity. I have withdrawn my application for astronaut training camp. I'm not
Oh no, really?
I know. I've given it a lot of thought. Now let's go to the problem of another small thing, and that's micrometeoroids or micrometeorites. These are tiny fragments of rock and metal traveling at speeds up to 70 kilometers per second, and they pose a kind of a silent threat to the moon's surface. The bombardment is intense, with estimated impacts of 15,000 to 23,000 per year from particles ranging from a millionth of a gram to 10 grams. Even microscopic particles can carry enough energy to damage structures or equipment over time. The moon's vacuum environment, of course, offers no protection, no atmosphere, making hypervelocity impacts a constant concern. Constant impacts create micro craters and eject fine dust clouds across the surface. So you have not only elevated dust from electrostatic charge, but from micrometeorite impacts. They can puncture habitat surfaces and degrade spacesuit integrity over time. Combined with adhesive dust, they create a compounding hazard to astronaut safety and equipment longevity. Researchers at Columbia University's Department of Astronomy led a team to investigate the risks of micrometeorite impacts on a proposed lunar outpost. So here are some of their research and their findings. NASA's Meteoroid Engineering Model 3, called MEM3, normally estimates micrometeorite risks for satellites and interplanetary probes. But the group from Columbia adopted it to model the risk for a lunar base, treating the habitat like a spacecraft fixed on the lunar surface. They assumed that Artemis Base would be compatible in size with the International Space Station, roughly 100 by 100 by 10 meters. And they ran simulations for 1,000 virtual bases dotted evenly across the lunar surface. The researchers calculated not only the rate of micrometeoroid impacts onto the moon base in different locations, but crucially, how many strikes might be expected to breach its shielding. The team found that a lunar base located near the moon's equator and on the longitude directly opposite Earth would experience about a maximum of 23,000 impacts per year. At this position, their model revealed that the focusing effect of Earth's gravity, bending trajectories and concentrating extra micrometeorites toward the moon, is more significant than the blocking effect from our planet. So that's near the equator. For a base located at the lunar South Pole, which is in fact where we're going to land, the impact rate is roughly 1.6 times lower, or about 15,000 impacts per year, which bodes well for the planned location of the Artemis landing and the Artemis base. They also calculate how big an incoming micrometeoroid would need to be to penetrate the base's wall if it had a state-of-the-art Whipple shield. Well, what's a Whipple shield?
Yeah.
A Whipple shield, or a Whipple bumper, is a hypervelocity impact shield designed to protect spacecraft from micrometeoroids and orbital debris. It was invented by Fred Whipple in the 1940s, and it remains the primary method for safeguarding crewed and uncrewed vessels in space. So that's what's used today. So with this in mind, the researchers found this critical mass to be 0.07 grams, or about 0.002 ounces. So fortunately for astronauts, 99.9997% of micrometeoroids are smaller than this danger threshold, demonstrating that the current shielding technology that we have, this Whipple shield, will be adequate for protecting a moon base. Taking into account the impact rate at the lunar South Pole, this would correspond to a penetration rate of about once every 42 years. Not too bad.
Wow. That's pretty good.
For micrometeorites. Well, so what do we do? What do we do about this? Mitigating lunar dust and micrometeorites involves advanced technologies and strategies to protect astronauts and equipment from these razor-sharp electrostatic soil and high-speed impacts. Solutions include electrodynamic dust shields, specialized surface coatings, advanced ingress suit ports and airlocks, and durable material designs to manage dust, along reinforced structures for debris protection, aiming to ensure the safety for long-term lunar habitation. And that's it. That's my presentation. I am not going to space.
Great. Thank you very much.
How many of our viewers are going? Oh,
So yeah, so it's nasty stuff, but there are solutions, basically.
oh, so you say. So you say.
Yeah, maybe.
Maybe.
Well,
Okay, Dave. Well, would you like to carry on with this theme of lunar dust?
sure thing. Yeah. So what I did was I was just going to look at what experiments we've run on the moon, various, mostly from Apollo, but what's been done on the moon that actually tells us something about the dust, and in some cases maybe doesn't tell us as much as we think, but there were a number of experiments. In fact, the very first experiment that was put on the moon was a little dust detector on Apollo 11. The ESEP, the early Apollo scientific experiments package, carried a seismometer and a dust detector, and that was it. Those were the only two experiments, because basically Apollo 11, they were only on the surface for 2.5 hours, and they had a very simple setup, which actually one of the pictures that Lou had showed it, where they basically set it out. Now the later ALSEPs, the Apollo Lunar Surface Experiment packages, which I'll talk about in a little bit, were much more complicated. They had a central station, and then they set up equipment with wires spreading out in all directions, seismometers, heat flow instruments, all sorts of particle detectors that they played out over the moon. And it ended up taking a half a day or longer for these to do it. But of course, on Apollo 11, the idea was, walk on the moon, take a picture with the flag, get some samples, and the putting something down on the surface was almost an afterthought. So they had this ESEP. But anyway, one of the things was a dust detector. And it was called dust detector is simple. It was called the Dust Thermal and Radiation Environment Monitor, because it was basically measuring all those things. And that's one of the advantages of it, but also one of the drawbacks, because it couldn't really distinguish dust from other effects. But in any case, it was quite a simple experiment. It was just 3 solar cells that were placed on a little box, and if you can see it there, it's with the little circle, with the little red circle there. That's the box on top. That's on the ALSEP. That's not the ESEP, but it's the same. It was the same exact box, little box. It had 3 identical solar cells. One of the solar cells had no covering at all. One of the solar cells, they actually pre-irradiated it by putting it in a chamber and blasting it with a measurable amount of particle radiation to damage it. And then one that was just the regular solar cell covered with glass. And the idea of pre-irradiating one was to try to be able to tell what was the effect of radiation on the cells, damaging the cells, versus what was the effect of other things. And basically dust and thermal were the main things that would be affecting it. And if you even solar panels on your house or whatever, that they degrade over time, and they degrade just because they're getting old, probably mostly because of temperature. They get hot, they get cold, and that's kind of rough on a regular solar panel. So the radiation effects, in other words, even if you see a cell degrade with time, you don't know that it's dust, I guess is basically what I'm saying. They're going to degrade anyway. But the idea was that the voltages generated by these 3 cells would be measured, and actually the measurements were sent back every 54 seconds for up to 7 years for the Apollo 12 at least, and another 5 years for Apollo 14, and just a continuous measurement of how much power was being generated by these cells, which was basically telling you how effective they were, and partly at least how much dust was getting on them. Although again, it's hard to separate that, but I'll get into that in a minute. So what happened was, and this is a close-up of the DTREM, which was what was flown on Apollo 11 and 14. It was also meant to fly on Apollo 13, but obviously never made it to the moon's surface. and a different dust detector was flown on Apollo 12, which I'll talk about. But this was basically the setup. It was pretty simple. 3 solar cells, and like I said, one without a filter, one was pre-irradiated, and one just had a glass covering on it, which they call here a blue filter, but it was basically just a piece of glass. And what they found was measured over time. This is for Apollo 14. I should also mention that the Apollo 11 one only lasted for basically one lunar day, because the Apollo 11 was powered by solar cells. The later Apollo ALSEP packages were powered by radiogenic power generators, so that they could run for years and years. And in fact, we're still running when they were turned off in 1977. But that's another story. In any case, so you can see what happened with this, and it's very interesting. The blue line is the uncovered cell, and not surprisingly, that cell deteriorated fastest. Obviously, having the glass cover on it, presumably the main protection of that was from radiation. It wouldn't have had any effect on how much dust was being deposited on it, or probably not. Now, we don't know exactly how the dust behaves electrostatically, and it's possible, that the glass, an uncovered cell or the glass covered cell might somehow, repel dust or attract dust, or it may behave differently. But in general, the idea is that it was probably mostly radiation effects. Again, thermal effects also. The glass wasn't insulated or anything, so the glass wouldn't really have much effect on the thermal environment of the cells either. And interestingly enough, of course, the pre-irradiated cell, which is the red one, shows the least degradation. So very indicative that radiation is an important effect on basically lowering the capacity of these cells. And then the regular covered one, the green line, is obviously degrading, and you can see the cell output over time. The fluctuations are due to the position of the moon and the Earth, and when it's closest and furthest from the sun, just as part of the Earth's orbit. But these would be the maximum daily cell outputs from a solar cell, because obviously it changed completely over day and was 0 at night. So it was, we just measured the maximum output for each lunar day over all these years. And so anyway, there's degradation, and the big question is how much of this is due to dust, and if it is due to dust, how did the dust get there? Now we know, and we talked about micrometeorites, not only damaging surfaces, or not only damaging possibly even habitats for humans, but also kicking up dust. In other words, these micrometeors traveling at this speed, a lot of kinetic energy would hit the surface and would presumably knock up pieces of dust up into one of these sort of ballistic airless trajectories, and they would land somewhere. And some of these things could have landed on the solar cells. The other way dust could get there, this is somewhat controversial, but it's definitely being studied, and it's definitely thought to be a possibility, is electrostatic levitation. I wasn't going to go into that in a lot of detail, but the idea is basically that the ultraviolet radiation, and especially at the terminator, in other words, at the change from night to day or day to night, that it's possible that charging of some of the surface would cause some of the dust to actually levitate and then come down somewhere else. Now the one problem, of course, with that is it's hard to picture dust building up from levitation, because the next day or the next time it gets charged, it's going to levitate away from where it is. So it doesn't, it's hard to picture that being a mechanism for dust buildup over time, but it could be. So anyway, that was what the DCHEM found. And again, the main point is it's very hard to distinguish between thermal effects and dust effects mainly. It looks like radiation effects are are real. Oh, I did want to mention one other thing, and you probably noticed this in this image, the sudden for the blue line where it says solar flare, that sudden drop in the solar cell. It was a very sudden, very permanent drop, and what happened was in August of 1972, on August 4th, between Apollos 16 and 17, there was a major solar event, and when it hit the moon, it damaged all three cells, but the uncovered one obviously got the brunt of it, and it just it damaged it more, in that one in a day basically, or a few days, than how much damage there was over years really of time for a solar cell. So that's another that's interesting, not related to dust necessarily, but a very interesting thing that happened. The Apollo 12 dust detector, and I'll just go over this really quickly, was a mounted on the ALSEP Central Station, which, okay, well, the sentence got broken up. But in any case, that's the again, the Apollo Lunar Surface Experiment Package, and the Central Station is the big box that ran everything. It had three solar cells, but it had one on top and one facing west and one facing east. This one is particularly hard to judge with the effect of dust, but there wasn't a big difference between what you might expect, the upward facing one maybe being more having more ability to collect dust than the ones facing sideways. But then again, we don't know about dust, how it would cling to a surface, vertical versus horizontal. So it may be, it may not, you may not expect a difference. It's hard to say. But these are experiments that would be great to be repeated again. Similar kinds of experiments with a little more thought put into them to try to determine something more about the dust environment. I think it would be a useful thing. So anyway, these told us something about the dust, but some of it maybe not. And there's been reported articles about the lunar dust problem solved by these experiments and stuff, and I really don't think it's true. You just can't really distinguish between dust degradation and thermal degradation is really the bottom line. Now, in Apollo 17, they had a much more sophisticated experiment called the Lunar Ejecta and Meteorite Experiment. And this consisted of, well, this little box you see, and you can see how the central station was set up. That box in the back on the left-hand side of the picture there, right there, is the central station, and it has an antenna that pointed to the Earth, so it could send all this. And then it was connected by these cables to various experiments that were set over the surface. And right in the foreground there is the LEAM experiment. And you could see on the right-hand side what the experiment looked like. There were these grids, and I'll show you a little better on a diagram. But these grids with 16 basically squares on each of the three grids, one on top and one facing east and one facing west. And when a particle would hit the grid, it would generate a charge. And then there was a second grid behind the first one with 16 squares that was placed a short distance away from it. And that grid would also then respond when it was hit, so that you could actually see which square was hit on which of the two grids and get a general direction. And what the particle would do when it hit the grid was generate a small charge. And the charge would be proportional to the energy, the kinetic energy of the particle that it had. So you could tell something. You couldn't tell the mass or the velocity, but you could tell the combination of the mass times the velocity squared. So you would know something about certainly the amount of energy that the particle was bringing to the when it reached the detector. And then it would go through. It would generate a charge on both things, and it would measure the charge. And it would basically use telemetry to, let me get back to that in a second. Yeah, we use telemetry to, we'll just send back these hits, the measurements from these hits. But what they found with this, which was really surprising, was there would be readings that showed very high kinetic energies. In other words, a large electric charge that it would pick up, but it wouldn't be on the back sensor. It would only be on the front sensor. So, and also I should mention there was a microphone also. So a large enough particle would actually also trigger a microphone to that it could tell at a certain size. They could say, oh, this particle had to be bigger than this because it would trigger the microphone. But the particles would give an indication of a kinetic energy that should have been able to reach the bottom sensor, but it did not. And there were a lot of these, and it was really a mystery why something that had this amount of kinetic energy based on what the charge was didn't make it to the bottom sensor.
Interesting.
And it turned out that at least one of the ideas was that it actually wasn't a particle hitting the sensor. It was actually dust that was electrostatically charged that basically floated over the sensor or just kind of dropped on the sensor and imparted its charge to the sensor, which it detected. And, yeah, right. And it detected that and basically said, oh, look, this particle is hit and it generated this charge based on its kinetic energy, but it actually wasn't. It was just a particle discharging, and so it never reached the bottom sensor. It would just sit there or just float over, and so they got these readings. So this is thought to be at least an indication that maybe there is levitated dust floating around.
Right.
And another thing that was really interesting of that is, and maybe the whole idea of levitated dust is a whole another topic. But in any case, that when they did look at over 22 lunations, 22 lunar days, they looked at these how many events there were in basically 3-hour packets, and you can see around sunrise, it's a huge spike in these events. And also there is a small spike at sunset, but at the times when the electrostatic environment was changing rapidly, now there's no reason you'd expect more necessarily more micrometeorites or in other words, other mechanisms of dust striking or landing on this detector. No mechanism that anyone really can think of that would, be so much more effective at sunrise than other times. And so this is also, given us an indication that perhaps there is some dust levitation going on, and it's triggering these events. Anyways, it's a very interesting idea.
I noticed that it's particularly from the east sensor as well.
Yes, that's right. Thanks. I did want to mention that, and I've forgotten. So yes, you're right. The east sensor. So facing the sunrise. It seems to be getting it, and the west sensor obviously has the least. So it's interesting circumstantial evidence. And then one other thing, and we'll go back to Surveyor now. So back even before Apollo, there were these images taken by Surveyor either right after sunset or right before sunrise that showed this horizon glow that they called it. And one of the possible explanations is that there is a little layer of levitated dust, and it's just reflecting the sunlight over the horizon, because obviously there's no atmosphere on the moon. There's no reason to be expecting that you would get a glow like this, like we're used to on Earth at twilight. But there's no reason to expect anything like this on the moon. And so a possible explanation is that is also levitated dust. Anyway, those are pretty much all the things that we looked at on the moon in situ that had to do with dust, and I just thought I'd make a little mention of those things and talk about them a little bit. So yeah, thanks.
Thank you very much, Dave. Thank you. They're most interesting. It's
very interesting.
Amazing how you know, we think of lunar dust. Well, thank you to Lou as well, of course. But it's, you know, think of lunar dust and like it's nothing, but it is consequential. And I'm just amazed that back in the late 60s, those detectors worked as they did, because they seem pretty far advanced, really, in terms of...
Right, well, yeah. But I mean, the certainly the little dust detector with the solar cells was very simple, but that LEAM instrument was quite a thing, and I actually got to meet Otto Berg was the principal investigator, and I actually got to meet him a couple of years before he passed away. We visited him at his house because he had these notebooks with all this information about these LEAM instruments that we wanted to archive, and so I got to meet him, and it's fascinating, you know, just fascinating.
Wow.
Just meeting him.
What an amazing
time
time.
This.
Yeah. Well, thank you both very much. Very, very interesting. Okay, before we go any further, quick word from our sponsor. This video is sponsored by Picastro. It's like Instagram for space nerds. Well, as ever, a big thank you to Tom McCrory for sponsoring Space Oddities. If you are an astrophotographer and haven't yet joined the Picastro community, you should do so, because it's growing fast, and you will have a lot of fun and find a lot of people with similar interests. Okay, so how are we doing in the chat, guys? Is everybody happy? Yeah, lots of chat. So Ian says, someone get Lou's coat. Listen, we've been trying that, Ian, for a very, very long time. We've not managed to find it yet. But we do.
To you like lunar dust.
Yeah, lunar dust. Yeah. So of course it was named after you. Okay, what are we going to do now? Just give me a second, and I'll just sort myself out here. I should have a slave to do this for me, of course, but unfortunately not. Right, here we are. All right, what I'm going to do is have a look at something which you may be familiar with, called the Hertzsprung-Russell diagram. Now, don't worry, because you know, it's not that complicated.
I remember it well.
Yeah, it has the reputation of being complicated. But what I wanted to do today is to take you through it, because it's important. Now, this is the Hertzsprung-Russell diagram. If you've never heard of it before, you're not familiar with it, don't worry, because I want to try and simplify it for you. And the reason I want to do that is that this is one of the most important diagrams in the whole of astronomy. I mean, you may see it portrayed like this, like this, like this, like this. There are lots of different ways you can draw this diagram, but they all contain exactly the same information, no matter how you draw them. And it may look complicated and confusing, but they're all really slightly different ways of portraying the same thing. The Hertzsprung-Russell diagram, or HR as we'll call it for short, the HR diagram, it's a visual way of understanding the life cycles of stars. It's one of the most important and well-known diagrams in astronomy. Now, we're going to simplify it so that, you know, it becomes easier to understand. It will be a simplification, because there are different things that you can add to the diagram to make it complicated, but we're going to keep it simple, at least initially, so that you can understand what the diagram means and what it's telling us about the life cycles of stars. But before we do that, let's start at the very beginning. The diagram was the result of work by a Danish astronomer called Ejnar Hertzsprung. Forgive my pronunciation if there's anybody watching in Denmark. who lived from 1873 to 1967, and the American astronomer Henry Norris Russell, who lived roughly at the same time. They were contemporaries, 1877 to 1957. Now, they did important work on stellar evolution, how stars change as they age, which led to this diagram. It's important to note they didn't work together because Hertzsprung was in Denmark and Norris in America, but they both contributed important ideas so that the diagram is named after both of them. They were working on similar ideas. And let's look at this in a bit more detail. Now, Hertzsprung first recognized the distinction between giant stars and dwarf stars somewhere between 1905 and 1907, while analyzing stellar spectra and brightness. But he did publish his work in relatively obscure journals, including the German journal entitled something unpronounceable in German, which many astronomers did not regularly read. I'm not even going to attempt that one. A few years later, Russell independently plotted stellar luminosity versus spectral type using newly measured stellar parallaxes. When he presented his diagram in 1913, the giant dwarf separation became visually obvious. So for the first time, astronomers could see that there are two distinct populations of stars and separated dwarf stars and giant stars in a visual way. Now, at that point, Russell, who hadn't been aware of Hertzsprung's work before that, became aware of it. And the astronomical community recognized that Hertzsprung had basically said the same thing as Russell by making this fundamental distinction between dwarf stars and giant stars. And therefore, the diagram was named the Hertzsprung-Russell diagram to acknowledge both contributions. Hertzsprung first recognized the giant dwarf stellar populations, and Russell produced the clear graphical diagram that made the relationship obvious. And when asked about it, because initially what the astronomers wanted, or there was a move to name the diagram after Russell, but he said, no, I've got to acknowledge the contributions of Hertzsprung. So the diagram became known as the Hertzsprung-Russell diagram. Let's talk about stars before we go any further. Okay, team, here's one for you. Give me some properties that stars might have, or all stars have, I should say.
Well, luminosity.
Okay, that's the first one. Yeah.
Density.
Density is one. Yeah, haven't got that on my list, but never mind.
Lifetime.
Yeah.
Let's say mass.
Mass, right.
Okay, any others?
Surface temperature.
Surface temperature.
Yeah.
Okay, well, let's go through the list that I've got. So we've got brightness, spectral type, radius, the size,
Radius, yeah.
temperature, metallicity, basically the composition of the star, rotation rate, magnetic field, surface gravity, and mass. I mean, you know, you can add others. Which of those properties would you say is the most important?
Mass.
All right,
Well,
Lou
I would
says mass.
say-
Any other ideas?
I would say brightness.
Brightness.
If we're referring to the Hertzsprung-Russell diagram.
Yeah.
And temperature.
Right, brightness, temperature, mass. Any other ideas? Okay, so just bear all this in mind, that stars have lots of properties that you can measure and you could plot on diagrams. Yes, we all agree with that. Yeah. Yes. Yes. Okay. When we talk about spectral type, we're talking basically about the color of the star. And stars go from blue stars down to orange-red stars. And they are given a class, O, B, A, F, G, K, M. Where's the sun in that range?
Isn't it G?
G.
Yeah, it is. The G stars are classed as yellow stars, but in fact, the sun is not yellow. It's white with a touch of yellow. It only looks yellow because of our atmosphere, but the sun is actually a white star.
Could I just make a quick comment? I had wondered about what color is the sun.
Yeah.
And I was working in the heliophysics branch, code 670 of Goddard Spaceflight Center, NASA's Heliophysics Center of Excellence.
Oh,
The highest concentration of solar heliophysics scientists, perhaps, in the world. And I just went around and asked them, what color is the sun? I got 4 different answers. Maybe 5 different answers. So I don't know. I carry on. I just wanted to make that small.
I bet you got some funny looks, didn't you?
I did. Oh no, they're scientists. They're so excited about talking about.
Oh, of course.
Here it is, and if you look at the black body curve here, and
yeah,
they were just so engaged. It was adorable.
Yeah, I'm sure. The yellow stars do form within a range of colors, ranging from white to actual yellow, but the sun is more towards the white end of the spectrum. And as I said, it only looks yellow to us in the sky because of the atmosphere, basically. Okay, we also know that the sun is a G-type star because of its temperature. Because if you look at the temperatures of these spectral types on the right, you'll see that the yellow stars fall from within the range of 4,900 to 6,000 degrees Celsius, which is, the sun is at the upper limit of that. The surface temperature is 6,000 degrees Celsius. But the important thing to note here is that what spectral type a star has can depend on a lot of different factors, yeah? And hence their temperature can depend on different factors. But we'll come back to this in a little while. So how does this relate to the Hertzsprung-Russell diagram? So what Hertzsprung and Russell did when they created the diagram, although they were contributing, roughly the same thing, but not working together on it, they simply mapped the luminosity or the brightness of a star against its temperature on a graph. And here we can see the axes of that graph. On the left-hand side, we've got the brightness going from dimmer stars up to brighter stars, and the luminosity, the temperature going from hotter stars to cooler stars. Now, that is a fairly straightforward thing, but that is basically all that the Hertzsprung-Russell diagram does. It maps the brightness of a star against its temperature. And when Hertzsprung and Russell both did this, when they put these spectral types onto the Hertzsprung-Russell diagram, this is what they found. A band going right across the diagram with the hot blue stars at top left, going down to the cool red dwarf stars at bottom right. And each one of these is a different spectral type, which are given along the bottom there, just for reference. You don't have to put them on the diagram at all. This band that Russell saw across this diagram, he called the main sequence. Now, most stars, including the sun, lie on the main sequence. And as you can see here, in terms of surface temperature and luminosity, brightness, one of those is the sun, the G-type star I've indicated with the sun there. So we've got hot, bright stars at the upper left, cool, faint stars sit at the lower right. And as we can see, we've got the spectral type along the bottom. But it's important to note one very important thing. This is not an evolutionary track. This is not the evolution of stars. It's a family of stars with different masses that are all doing the same thing. And what is this thing? What do main sequence stars have in common? They are all fusing hydrogen into helium. So if a star is on the main sequence, it's burning hydrogen, essentially. So the left-hand side contains massive stars, mediocre stars like the sun in the middle, and the right side contains red dwarfs. So this is not a time sequence, it's a mass sequence, okay? Okay, or I hope that's okay. Viewers, if you have any questions as we're going through this, don't hesitate to put them in the chat, please, and I'll answer them afterwards. Or perhaps if we do get any questions, somebody will be kind enough to read them out for me because I can't see the chat from where I am. Okay, let's move on. But another thing we could do is add that main sequence to the diagram in a different way. We could, for example, plot mass against longevity, how long a star lives for. So as you can see, high mass stars, more massive stars, last a lot shorter time. They have much shorter lifetimes than long-lasting, less massive stars like red dwarfs, which last, potentially red dwarfs can last for trillions of years. They can outlive the universe, or the current age of the universe. So we go from stars that are massive, that burn out and use up their hydrogen very quickly on the left, and low mass stars that can last a long time on the right. So that would be another way of plotting two of the properties of stars. We could do it another way. We could map size against longevity. The bigger stars on the left-hand side having the shorter lifetimes, and the smallest stars having the lowest or shortest lifetimes. Why is the difference? Obviously, supergiants, the hottest stars, burn through their hydrogen faster in a few million years, whereas red dwarfs, the most common type of star, comprising 3/4 of the star in the Milky Way, for example, are much cooler and therefore burn through their hydrogen much slower. And this is another way of representing two different properties of stars on this diagram. So where does that get us? Well, we haven't finished with this diagram yet. So here's the original diagram, luminosity against the surface temperature of the star. And we need now to add another population of stars to the diagram. And this is known as the red giant branch and comprises stars, as you can see, which are red, giant, bright, and cool, like the famous star Betelgeuse in Orion, for example, that red giant. These stars have run out of hydrogen and are burning heavier elements like helium, carbon, and oxygen. They are therefore not on the main sequence. They're not burning hydrogen anymore. They've got past that. Hydrogen's old hat. They now moved on to more exciting elements like carbon, helium, and oxygen. The destiny of our sun is to expand into a red giant star as it begins to run out of hydrogen in about 4 or 5 billion years. It will then leave the main sequence and ascend to the red giant phase like that, where it will remain in total for about 1 billion years. However, within this billion-year period, it will go through several distinct phases. So within the red giant branch, you've got evolution in time in different phases, which I haven't added here. But let's just call it red giant branch. The sun will ascend to the red giant branch in 4 or 5 billion years and will stay there for about 1 billion years and go through different phases. Now, the next population of stars we're going to add to this diagram is the white dwarfs. These are hot, white, ultra-dense stars and represent the final stage in the life of a main sequence star like the sun, or at least most of them. After 1 billion years as a red giant, the sun will slowly shrink, leave the red giant branch, and move into the white dwarf population. So it will move from the red giants down into the white dwarf population. Now, not all stars will do this because, team, what does it depend on what happens at the end of the red giant phase?
Basically, the mass of the star.
How much mass, right?
Stars, because ultramassive stars will explode as supernovae and go on to form either a neutron star or a black hole. Those that have less mass, like our sun, will move into the white dwarf population. Okay, I hope that's okay so far. Now, let's add one final group of stars to our diagram, the supergiants. An example of a supergiant is Rigel in Orion, for example. And it's a star that lies in the upper region of the diagram with luminosities typically 10,000 to more than 1,000,000 times the sun's luminosity or brightness. These occupy the top band of the diagram, extending across a wide range of temperatures. Supergiants are usually late evolutionary stages of massive stars that have expanded dramatically after leaving the main sequence, and they can appear right across the top of the diagram. So we have different types of supergiants. We've got blue supergiants, which are the hottest at the upper left of the diagram, yellow supergiants of intermediate temperatures, and red supergiants on the right, top right, which are cooler. And although the HR diagram defines them by luminosity, supergiants generally have radii tens to over 1,000 times the sun's radius. And they have masses between roughly 8 to 60 solar masses. They are truly, obviously, excuse me, giant stars. And because of this, their surface gravity is extremely low compared with main sequence stars. So we've got some examples on this diagram. We've got Arcturus, we've got Antares, we've got Betelgeuse, we've got Polaris, the pole star, we've got the sun, obviously, we've got Rigel. So as you can see from this diagram, it allows you to trace the life cycle of stars. Most stars will start off on the main sequence, burning hydrogen, then ascend to the giant phase, and if they don't go supernova because they're not massive enough, will end up as white dwarfs. Supergiants have a slightly more complicated life cycle, but you can get all the information you need from this diagram. Now, that is a typical representation of an HR diagram. And that is how you always see this diagram, or slight variations of it, as we've seen portrayed in books. But I had an idea, and I'm quite thrilled about this, actually. And I thought to myself, well, we've said that mass is a very important component of a star, a very important property of a star. So I thought to myself, what if we add mass into the diagram as well as luminosity and temperature? What if we were to make a diagram that showed luminosity, temperature, and mass? Because it turns out that mass is the most important property that a star can have. It dictates all of the others. And if we did add stellar mass, the HR diagram allows us much greater insight into stellar evolution and reveals truths we would not have seen otherwise. So after messing about with AI for a bit, I produced the following picture. This is the HR diagram with temperature, luminosity as our X and Y axes, but also adding a third axis, which is mass, and you end up with this beautiful cube. And this contains some very, very interesting information. So let me talk you through this. So using the sun as an example, what we saw in the 2D HR diagram, that it follows a path, a straight line, if you like, through the main sequence up to the giant phase. But in this 3D representation, its mass is also changing, of course, as it's moving through that line from the main sequence to the red giants at top right. And because its mass is changing, it's moving, if you like, towards the back of this diagram, towards the back wall of this diagram. So it's moving through space, a three-dimensional space. Its temperature and its mass and its luminosity are all changing at the same time. Now, if you look at the main sequence here, in the traditional diagram, the 2D one, the main sequence looks like a thin line. But when we add a third dimension of stellar mass, we see really that the main sequence is not a line anymore, it's a surface. So mass controlling a star's internal pressure and temperature, which in turn determines how fast the nuclear fusion takes place. That sets both the star's luminosity and its surface temperature. Now, because different masses produce slightly different combinations of temperature and brightness, stars don't fall on a single mathematical line. Instead, they occupy a narrow sheet of stable solutions where gravity and nuclear energy are in balance. So the stars on the main sequence are stable. They're fighting against the force of gravity trying to compress them, using their nuclear energy to exert outward pressure. So these are stable stars. But because, as I said, in different combinations of temperature and brightnesses, they're not on a line anymore, they're on a surface. And what this surface represents is all stable hydrogen burning stars. So where do we go from here? Now, let's just see what else we can pull out of here. Now, talking about this surface, a star's position on it is mainly determined, as we said, by its mass. Small stars sit at the lower part of the surface. They are cooler, dimmer, and can live for trillions of years. As we move upwards along the surface, we encounter more massive stars. These stars burn their fuel much faster and shine more brightly. Eventually, stars leave this surface as their internal fuel changes. Sun-like stars move towards the region of red giants, becoming cooler on the outside, but dramatically brighter. More massive stars expand even further into supergiants, the ones we've talked about, some of the largest stars in the universe. At the end of their lives, stars collapse into compact remnants, such as we've talked about, white dwarfs, neutron stars, or black holes. Now, what this diagram reveals is that stars follow predictable paths through this space of temperature, brightness, and mass. And the most important factor guiding them on that journey is one single property, the mass that the star is born with. And only by adding stellar mass as a parameter to the HR diagram, as I've done, can we truly see what the diagram is telling us, that mass is the property of a star that controls all of the others. Now, you can take this one step further, which is what I did. Now, I warn you, this diagram does look confusing, but let me just briefly show it to you. And this three-dimensional space that stars move through on this diagram is known as stellar parameter space. So again, we've got the surface of the main sequence, not a 2D line as in the 2D diagram, but a surface comprising stars of different temperatures and brightness. And then you can see on here, we've got the supergiants, we've got the planetary nebulae, and we've got the red dwarfs, those long-lasting, cool, small stars at bottom right. Now, you've got lines on here that link some of these stars. And again, it's important to say that this is not an evolutionary path. This is linking stars of similar mass and temperature. And we go from short-lived stars at the top left to the longest-lived stars, the red dwarfs at the bottom right. And the stellar lifetime there is, I've put along the bottom, billions, millions, thousands, and trillions of years. So we come to the end of that, but just want to answer a few questions as we go through it. Why does the HR diagram work? Well, firstly, it allows us to visualize the life cycles of stars rather than just study facts and figures. A picture's worth 1,000 words, as they say, and which is why Russell, when he first drew the diagram, was amazed to find that he could visualize the main sequence on it. It clearly shows that stars are not randomly placed in their life cycles. The diagram shows correlation because stars follow predictable paths along narrow tracks in the diagram. They're not free. Stars are not free to appear anywhere on that diagram. Physics constrains exactly where each star appears in the diagram. Stellar properties like luminosity, temperature, longevity, mass, and others can be mapped against each other in different versions of the same diagram. All are interdependent, but the one controlling factor, one property to rule them all, if you like, is the mass a star was born with. Adding this to the diagram and showing it in 3D allows us to get insights into the relationship between mass, temperature, luminosity, and so on very clearly, and to clearly visualize exactly what's going on. And it's this interdependence of stellar properties that makes the HR diagram so compelling and so useful for understanding the life cycles of stars. And it's also important historically because it was the first visual representation. It showed clearly for the first time that stars do evolve. They do change over their lifetimes. And that, ladies and gentlemen, is why the HR diagram is so important. So I hope you enjoyed that. If you have any questions, don't hesitate to put them in the chat. And there you are.
Yeah, that's very interesting, Andy.
Yeah, thanks, Andy.
Some people were worried that you actually have ideas. So, but I told you I did say there will be an inquiry.
That was a much
I mean, one thing I've got. Well, you know, the problem I have with the diagram, and I almost slipped up earlier, is if you remember on the radio, I was forever calling it the Herschel sprung.
Yeah.
Diagram. But one thing, I mean, as you said, it literally shows the evolution from the beginning to the end of a star's life. And as you said, it's a dynamic diagram. It doesn't stay the same. The stars will move around within this, along the main sequence, and they will move up into the red giant stage, and then of course, like stars like our sun will drop down and become a white dwarf. So they're constantly moving. There's constantly things going on. But if I may, just one thing that this diagram was also used for, and that was to study clusters of stars. And what they found is I mean, as we know, these clusters, these type clusters, they are old. They are old. Some of the oldest stars in the in the galaxy, and that's what forms these things. And so what they did is they looked at all the stars, and they used the same thing for the Herschel-Russell diagram to plot them on there. And what they found was, yes, the stars come along, they follow the nice main sequence nicely. The real, when they first, when the stars really start off, they're really bright, and then they slip down the main sequence, then go through their main stage, and then they go off into the red giant stage. What they found is that there were some really bright stars that were lingering, they were hanging about, and they called them stragglers. And of course, they became known as blue stragglers because they sat at the top end, just above the sort of where they turn off to the red giant stage. So you had all these blue stars, and at first they didn't realize what they were, and it was due to that, so that these blue stragglers, and they in the end, what the main thinking is now, and Fred Hoyle was one of the chaps who come up with this theory as well, was that they are these blue stragglers are stars that are sort of like what they go off, they collapse down, and then become sort of like a white dwarf. But they also have a companion. They're binary stars, and this companion will then start to feed mass back onto the white dwarf, and again, so it will flare up again, and it will push it back up the main sequence. And sort of like basically, it's like a new star being born again, but it's the same stars doing this thing. But it's a very, very interesting diagram. I love the Herschel-Russell diagram.
But in fact, when Sirius B was discovered, this being the from our point of view, companion to the star Sirius, which, as you know, is incredibly bright and does drown out its companion a bit. When that was discovered and plotted on the Hertzsprung-Russell diagram, it didn't make any sense because it appeared at bottom left of the diagram, or sort of a little way up. And nothing like this had ever been seen before. And it was the first white dwarf to be discovered. Which is why it made no sense, because nobody had actually seen a star with these properties before, with the same sort of size, luminosity, temperature. So, you know, this is why the HR diagram is so very, very important.
Yeah. I mean, one thing that wasn't mentioned, but again, I mean, it would just complicate things if people are just learning about it. But you've got what they call the instability strip.
Yeah.
That's also in there. And this is where stars move backwards and forwards along from hotter to cooler, and also from blue to red. And they keep moving back. And of course, these are the variable stars.
Yeah.
And you've got the Lyra stars.
And Barry says, and put it up on the screen, Barry says they can also estimate the age of open clusters using the HR diagram.
Yeah.
Indeed, they can, Barry. Yeah, there are all sorts of things you can do. And Ian says, what about 4D? Well, yes, I mean, you can go on adding properties of stars. And I did a 4D diagram, but you get to a point where it really doesn't make much sense anymore. It's too confusing.
That's what one thing.
That was a much more detailed description of the HR diagram than I did at O-level astronomy.
Right. Oh, great.
Yeah.
Well, thanks for that.
Okay. No, I like the three-dimensional, or when you included the mass, but I'm guessing, and being a planetary person, not so much an astronomer, when you're looking at a star, except for supernova or things, the mass stays pretty much the same throughout. I mean, its lifetime.
Yes,
so that on that diagram, the evolution of a star would just stay on the flat plane.
Yes.
At one mass, right? And it would be constrained to that plane. Okay.
And
Interesting.
the brilliant thing is, its position on that plane is constrained totally by the physics.
Exactly. Right.
It cannot be anywhere else.
Yeah.
Can't go anywhere else.
I'd just also like to say, the reason that the supergiant blue stars, their life cycle is so short, is because, again, down to mass.
Yeah, absolutely.
Because it is burning its hydrogen so fast and so quickly to maintain its structure.
Yeah.
To maintain the outer pressure of all that mass trying to push in again.
Yeah.
So that's why they dissipate a lot quicker and pass away a lot faster than like the sun, which is going to be around for a few billion years yet.
Yeah.
So really, then, with the I'm getting away. I don't know. I mean, the bottom line would be that for a given mass star, then basically the difference would be sort of how much hydrogen, helium, and everything else is in the star, and that's, I mean, so between those two things, does that determine everything? The luminosity, the size? I mean, is that the temperature?
Mass determines everything.
Right, but over time, the amount of the star changes because the amount of hydrogen changes to helium.
Yes, exactly.
So, in other words, is that then the second determining factor? I mean, in other words, there's mass. If you knew the mass and you knew the percentage of hydrogen, helium, and everything else in the star, would you basically then be able to point to exactly where in your three-dimensional diagram that star should exist? Yeah, I think so. Okay.
Yeah.
I mean, also the star. Just looking at the star, it will tell you.
Yeah.
So,
I mean, you know, the mass dictates also the rate at which the nuclear fusion will happen.
Oh, exactly. Right.
And therefore, how quickly it will use up its nuclear fuel.
Yeah.
So
yeah. Okay. Yeah.
Yeah.
No, at any point in time, I guess I'm saying.
Yes, at any point in time, yes.
And then the hydrogen, helium. Okay, cool.
Yeah.
I mean, of course, as Andy was saying, as they get older, once they've burnt their hydrogen, they then start burning the other elements that they've actually started to forge.
Yeah.
And then you get what they call shell burning as well.
Yeah.
Because it will start burning, say, helium, but outside there'll be an outer shell of hydrogen, And what that means is the helium to burn needs more energy, more heat,
Right.
etc. And that will then pass on to the shell, and then the shell will ignite as well. So the helium will start burning again. And what they're doing is the star starts to pulsate as it works its way through. So, and again, this comes along the instability strip. Sorry, I got my old granddad finger. But yeah, but that's what it is. It basically it starts to pulsate
Okay.
as it burns through the layers. But once it gets to iron, then all bets are off.
Right.
Once it's used up its hydrogen, it moves off the main sequence.
Yeah.
And you know, it will, depending on what spectral type it is, it will move either to the giant phase, or it will stay there, depending exactly what type of star it is. For example, red dwarfs, as we know, can last for trillions of years. So their hydrogen is going to last for trillions of years, potentially, because they are low temperature. They have a much lower rate of nuclear fusion. So they will last, you know, much longer, and so on. Okay, there we are. So that's the HR diagram. If you do have any questions, put them in the chat. We are going to move on now. As time's getting on. So I think it's that time of the evening again. So yeah, so let's move over to the man who, as ever, needs no introduction. Let me put that up on the screen for you, Roger. Here we go. Here's our weekly look.
Hey, right. So here we go for getting through the first half of March already, and spring is rapidly approaching now. So here we are. We're working our way from the last quarter up towards the new moon. So things are looking a little bit less bright in the night sky, if there was ever a clear sky to look up at. But looking through the week, we can still see Jupiter quite nicely placed in Gemini, and we'd also have Orion, although it is starting to set now with the galaxy clusters of embedded into Leo and Virgo coming out through, and also some sites of the summer constellations coming up as the light goes on. But yay! But there we go. But during the week, just before sunrise and coming up, we've got Mercury and Mars coming up before the sun slightly, and following on behind, we've got Neptune, Saturn, and Venus. So the so-called planetary parade is well and truly gone, really, especially when you can't really see anything more than maybe Mars, Saturn, Venus, and Jupiter in the sky without any aid at all. But there we go. They are all fairly close to the sun, but there is an opportunity to see Mars, hopefully, and also Saturn and Venus, although Saturn is now rapidly becoming more of a low-down object after sunset anyway. So I think we can say almost goodbye to Saturn for the moment, although Venus will be a lot better to see as the weeks go on. So we've got, through this week, we've got an occultation, well, it was earlier on today anyway, an occultation with Antares at apogee with the moon. Jupiter ends its retrograde tomorrow, as is also the last quarter moon. And we've also got a little bit of play with Mars and Mercury, having a little dance in the night sky fairly close together. And on the 16th, we've got Moon at perihelion, and it will be at its closest this 2026, which is quite not a lot of people know that.
No, indeed.
And in fact, it will be at 363,300 kilometers. If you wanted to have that bit of information. So we're currently having a retrograde today and well, tomorrow through the night, and will be quite interesting to start to see it move out of Gemini. So it will be for the moon at perihelion on the 16th. It will be roughly 7% larger. So some people might be calling it a super moon or something, but we won't go there. No, we won't mention that. But some solar activity. There has been some spots over the last week or so, and we've got some just going over the western limb, and we have got some returning over on the eastern limb. A little bit of prominence activity, but as you can see on the right-hand side, we do have a little bit of a corona hole coming around towards us. So there might be some activity coming our way in the next few days, possibly. We shall see. And just to top it off, we have a little gallery with just an image from me, and not a very recent one. I did take some pictures of Jupiter a little while ago, but the seeing wasn't as good. So I had to look through some of my earlier images, and this one's from the 28th of April 2019 with a slightly larger C11 scope, and this was what I managed to get.
Ooh.
Oh,
It's quite.
That's
It's
nice.
quite. It's quite interesting to see if I did a side-by-side comparison on how the belts of Jupiter have sort of evolved over this period. But looking at the red spot, there isn't that much difference in the size, although there might have been a small reduction in the size. But you know, it's not bad. Okay, so that's what we have for this week.
thank you very much, Rog. Thank you very much indeed. So, you know, if you would like to send your images into our gallery, then you can just attach them to an email, one image per email, please, and send them to gallery@spaceoddities.space. And, you know, do send your images in. I mean, we actually had to use one of Roger's tonight. And, you know, we don't want that to repeat, do we? So please get your images in. And, you know, let's see your images. And as we keep saying, they don't have to be taken with expensive equipment. Anything, any image you've taken of the night sky or anything related to it, then do send them into our gallery. Not only do you get to see them here on a Tuesday, but you get your own gallery on the Space Oddities website, which is, of course, spaceoddities.space. So there we are. Well, we're going to move on now. We're back to Dave now.
Yeah, Andy, let me interrupt real quick because I saw the thing in the chat, and this is what we were talking about earlier. When you change time, because we already changed time, and I see now so I guess you answered it there on the 20th of March, which means
it's actually the 29th.
Yeah, that's what I thought. That's what I thought you said earlier. It was
29th.
later, right?
It's the last Sunday in March.
Last Sunday in March.
Sorry,
Okay,
I put that in there. I was thinking of the actual equinox. So yeah, sorry.
Yes,
That's my bad.
definitely the Sunday the 29th.
Yeah.
So for
29th of March.
Yeah, 29th. Sorry, Paul. 29th.
For us here in United States, anyway, we just need to keep track that it'll be different by an hour throughout March on the Tuesdays throughout March, and then we'll be back on track. Okay. No, I know we had that confusion earlier, and so I just want to make sure everyone else knows too. Okay, good.
Yeah. Okay. So Dave, the week in, if you're ready with that.
Yep.
So as you may know, viewers, every week Dave does a look back at some anniversaries, basically, of interesting events in solar system exploration in past years, and he makes us all feel very old.
Yeah, some of these might. I think
I'm gonna.
There we go. Okay.
I'm gonna give up admitting to remembering some of these. So,
March 8th and 14th. No, one thing that's been surprising about this is the, and you'll see another one of these, kind of this funny serendipity of things that come on close together on calendar dates, many years apart, but are somehow related. And I'm kind of surprised sometimes when I stumble across these when I'm putting this together. Okay. Anyway, Yeah, March 8th to 14th. All right, so we are March 10th. All right, March 8th, 1979, and some of you might remember this.
Oh,
Basically,
Linda Morabito, yes.
That's right. So right on March 8th. So on 3 days before that, in 1979, on March 5th, the Voyager flew by
Oh yes.
Jupiter, and took all sent back all these pictures, and of course everyone was looking at the pictures, and Linda Morabito was one of the people working on and analyzing the images, and on her little ModComp computer, which is shown there in the picture right next to her, she saw the image which you see in the center there, with the little tiny plume up at about 10 o'clock, and recognized that this was indeed a plume from Io, a volcanic plume.
But
And,
sorry, Dave, before she did that, she thought it might have been another moon of Jupiter, because it does look like a
that's
moon
peeking out from behind. That's
Yeah.
right. That's right. I'd forgotten that. I remember
so
that
she-
now.
she-
Yes.
She
But
checked the ephemeris of all of the Galilean moons, and realized that it couldn't have been another moon of Jupiter. It had to be something
Right.
else.
Yeah,
That's
but then
right.
that's no moon.
Yeah,
Yeah.
exactly. That's no moon.
No, that's right. That's right. I'd forgotten about that. That's right. In any case, right. But what was also really fascinating about this, and one of the great science stories, I guess, or great predictive stories of science, is that only 3 days before the flyby, Pio, Casson, and Reynolds published a paper predicting that because of Io's orbit, because of the synchronicity with the other Galilean moons, and because of Jupiter's immense gravity, that the whole planet itself would actually be flexing enough that the tidal disruption would be heating the interior, and that it was very, very likely, even they said, I think, that the interior was molten. And so it's almost never happened that there's been a scientific prediction that's been basically proven within less than a week.
That's amazing.
Yeah, it really was, because no one thought this was really the case. Again,
No. And the
so
other thing,
anyway,
the other thing about Linda Morabito was that she was a fairly junior navigation engineer working on Voyager.
Yep.
And when you think that she wasn't anybody who anybody would ever remember, probably, but
right.
She secured her place in history by finding the first active volcanoes on another world. I find that amazing.
No, being in the right place at the right time, and being smart. I mean,
absolutely.
like you said, she thought it might be a moon, and she looked, she figured it out that it wasn't, and there you go. So I love that story anyway.
I do too.
It's pretty great.
I saw a photo of her recently, how she looks now. And,
oh, really?
Yeah, she looks older.
Well, she's got the great 70s hairdo there and everything.
Yeah, fantastic. Bring those days back. That's what I say.
But then again, you'd be using a ModComp computer, so think about that.
Yeah, that's true. Yeah, don't.
Okay, March 9th. So 1611, and this is great for all you observers out there. It's good. It's first sunspots observed.
Oh, wow.
Johannes and David Fabricius, a couple of Dutch astronomers, a father and son. Johannes was the son, who actually was sort of in charge of this particular observing thing. Saw what's pretty certain to be the first observation of sunspots, and very good advice on observing the sun with a telescope there. If you allow only the edge of the sun's rays to go until your eyes get used to the sun, and then you can look at it.
What?
Yeah, right, exactly. I mean, I kind of read that, and I figured you're probably having the same reaction I am. Are you nuts? I mean, obviously, 1611, not a terribly powerful telescope, but there's later on they're talking about how when they were observing the suns, their eyes were red and bothersome for up to 2 days afterwards.
Oh my God!
I know.
All in the name of science, eh? All in the name of science.
Anyway, I couldn't resist putting that in. I just thought that was amazing. But anyway, so still the first people to see sunspots. That's pretty cool. Yeah, that's pretty nice. And actually, this was almost to the day 7 years later. I think 7 years later on March 8th. Now I should have scribbled it down here. Anyway, was when Kepler discovered his third law, that the period of the orbit cubed is equal to the semi-major axis squared, or not equal to, but proportional to. And it was so it was anyway. It was interesting. Just that it was almost at this almost the same. I think it was a day earlier, but 7 years later that he discovered that. Okay, here you go. You guys have to love this. The March 9th in 2004, again, maybe feel a little old, but the Hubble Space Telescope, the Ultra Deep Field Image, was unveiled.
Wow.
And I don't think I need to say anything more about that. I just
wow.
I still look at this picture and I'm like,
yeah.
Oh my God. What can you say? So it's but quite a moment, I think, for everyone, where
and especially when Hubble was pointed to a supposedly empty part of space.
Right. And they just let it run for basically a million seconds. Obviously over a few periods, but
that's about 30 hours, isn't it? Something like that.
Yeah, definitely. Something like that.
Yes, right. And I don't know. It's like maybe in your head that there's all these galaxies out there, but when you see it, anyway, there you go. Okay. Oh, Comet Halley. Okay, 1986. So, yes, a great opportunity that almost every spacefaring nation at the time took advantage of, except one.
Which one would that be then, Dave?
Which one was
that? Because for the administration at the time didn't really support space research, the way that maybe should have been. Well, in any case, we missed out on this, but thankfully, the Japanese, the Europeans, and the Russians, or the Soviets at that time, I guess, did take advantage of the opportunity, and we did learn lots of amazing stuff about Comet Halley in particular, and comets in general.
Yeah.
March 8th, 9th, 11th, and 13th.
God.
We got to see all these guys fly by, and of course, And
Dave, can I just quickly tell you about? The other guys know this because they'll remember it. The BBC decided to do live coverage of the closest approach of Giotto to Comet Halley. And they set up this program in the Royal Observatory at Greenwich with a studio audience, if you like, and experts there to tell the public exactly what we were seeing in the images that were coming in live from the comet. And it was probably the most disastrous science broadcast in the history of TV, because I can't remember who was. Do you remember, Michael? Who was hosting that? I can't remember.
Was it James Burke?
No, it wasn't James Burke. No, because James Burke would not have asked such questions. I can't remember. I'll have to look that up. But anyway, the host was asking the scientists as we saw these images.
Yeah.
And of course, what Giotto was returning was brightness maps with each brightness color coded. And so you had a series of color bands and rings, and that's what was coming back from the comet. And the host was saying to the scientists, "What are we seeing? And the scientists were saying, "I've got no idea.
Yeah,
You
yeah.
know, we haven't processed the image yet." And then the host was getting progressively more nervous and more nervous because the same types of images just kept arriving one after the other. And he was going back to the scientists and saying, "What are we seeing? I don't know."
Yeah.
Oh, no.
And it was a terrible piece of television.
Oh,
And
no.
the scientists
Yeah, I
got
remember
really annoyed with the presenter in the end because all he kept saying was, "Can you tell us what we're seeing in this image? I don't know."
Oh, boy. Oh, boy. Oh,
Yeah.
yeah.
It was quite funny, actually. It was quite
Yeah.
funny. But there we are.
Oh, wow. Well, anyway, it was pretty great. I was, I remember I was in grad school then, and we'd gone down to we'd done a geology / astronomy field trip down to Baja, Mexico, to down in the peninsula to
Mhm.
get a nice dark sky to see Comet Halley, because of course it was never very bright.
Right.
And in this the most recent apparition, but we did get to see it. We had a pretty good look at it in really dark skies. It was good. And the picture on the left there, the lower left, is just such an iconic comet picture. I you just can't forget it. March 10th. Oh yeah, and you did mention this earlier too.
Ah,
March
yes.
10th, 1977, Uranus's rings first observed. The Kuiper Airborne Observatory, which was a NASA plane, which was down there, obviously in the lower right, and this little porthole you can see right in front of the wing, and they would just stick their instruments out that the plane would fly. They had all sorts of devices to minimize movement and turbulence, and Uranus was passing in front of a star, SAO something, I don't remember the number, 158647 or something, but and then in the upper, actually the picture in the upper right there is the chart recorder. Is an actual picture of the chart recorder when it was in operation on the airborne observatory while the rings were being occulted, or while the star was being occulted by the rings, and that was the actual observations coming back in real time, were being printed out on this chart. Of course, you would have gotten the same reaction at that point. It was, what are we looking at? I don't know. But once they processed it, they could tell there were rings there that it was passing through. And yes, yeah. Anyway, so 1977. So yeah, we're all right. Don't feel too old, but there you. Yep. Anyway,
I think the thing was about the BBC. They expected to receive photographs from the comet.
I realized that, and someone didn't tell them, or
they didn't ask.
Someone didn't realize. Right.
No, they didn't ask. So there we are.
Yeah.
But, oh my goodness me.
So this is funny. Yeah. This is the thing I was just talking about, right? March 13th, 78 or so, almost exactly 196 earlier, Uranus was actually discovered. And of course, the first planet ever discovered, because every other planet had been seen since prehistoric times in the sky. But Uranus, it was William Herschel, and it's just funny that only a few calendar days off from the rings being discovered, but 196 years earlier, the actual planet itself was first discovered. Yeah, thought it was kind of cool. And then Mars, lots of Mars stuff in March. March 10th, the Mars Reconnaissance Orbiter reached Mars and went into orbit exactly 20 years ago today. So there you go. 20 years ago from
Happy birthday, MRI.
Right now. Yeah.
And that has been an amazing spacecraft.
I know. And yes. The flood of data, I remember, was something we had to deal with. The planetary data system and at the archive was was pushing what we could deal with as far as archiving data and bringing in data and storing it and transferring it and stuff. Mars 6 in 1974, the descent module reached Mars, and this was the first ever Martian atmospheric data ever returned. So from 1974. And then 2016, so 10 years ago, was the launch of the ESA ExoMars Trace Gas Orbiter to Mars, which has been, operational also. And that is not all. Finally, last but not least, I guess,
Oh, yeah.
March 8th, 2004, first image of Earth ever taken from the surface of another planet. So Mars Spirit rover, and I don't know how well you can see that. You can't, even if you had a perfect picture on your screen, but that arrow is pointing to that little dot, and that's
I see
you.
that. Yeah.
That's you and me and everyone you know and everything you've ever
everyone that's ever
touched,
lived.
every place you've ever been to is right there. But that is from the surface of Mars, from the Spirit rover. That's kind of neat. So
wow, thank you, Dave.
yeah, that's what I got.
Amazing.
All right.
Yeah,
Thanks.
some of those I don't remember, like the discovery of sunspots in 1611. But funny enough. but a lot of them I do.
Still a little too young then.
I've never forgotten Ludo. So there we are. All right then. So to finish off, Michael is going to give us our constellation of the week for this week.
Yes,
so I will turn the floor over to him, and off you jolly well go, Michael.
Bear with me.
How are we doing for time? Oh, it's all right. We're a little over.
No, I'll be there shortly. When will I be there? It is.
Well, one thing before Michael gets started, about the HR diagram, I didn't tell you. The 3D representation I came up with, showing mass, luminosity, and temperature. You can look everywhere on the internet. You will not find that. I know. I've looked. It doesn't look like anybody's done it before. If they have, they haven't put it on the internet.
Well, there's a paper
You
for
saw
you.
it here first.
There's a paper for you.
Sorry?
There's a paper for you.
Yeah, absolutely. Yeah, toilet paper. That's probably all it's worth. But, so you saw it here first.
Yes.
First, I'm not saying astronomers have never mapped multiple parameters of the HR diagram, because it seemed to me that was the obvious thing to do. But I can't find any images of it on the internet. So you saw it here first. There you are. Okay, Leo Minor then, Michael.
Yes. Okay, well, this is tonight's constellation of the week. The lesser known Leo Minor. Most people have heard of the constellation Leo, which is just next door to Leo Minor, but it's a smaller counterpart in the northern sky. This was a newcomer among the stars. Leo Minor was created in 1687 by Polish astronomer Johannes Hevelius, one of the last great naked eye observers of the pre-telescope era. He filled in the gaps between larger, well-known constellation by cataloguing previously unnamed star groups. So thank you, Hevelius, for this one.
Indeed.
As said, not in the classics, ancient astronomers such as Ptolemy and Aratus regarded this region of sky as essentially empty, a quiet corridor between Ursa Major and Leo. Hevelius gathered 18 faint stars and gave this overlooked patch its identity, making it one of the youngest constellations in the modern canon. So there's another overview of where you find Leo Minor, Leo to just below, and Ursa Major just above, and Cancer to the right there. Leo Minor sits quietly in the northern celestial hemisphere, sandwiched between two of the sky's most iconic figures, covering 232 degrees. It ranks a modest 64th in size among the 88 recognised constellations. Best observed on April evenings at 9 p.m. thereabouts, visible from latitudes plus 90 degrees to minus 45 degrees, accessible to most of the world's population. So next month will be a good time to give a view. The stars that make up Leo Minor First, you've got 46 Neo Minor, Praecipua, I think. The brightest star, an orange giant of magnitude 3.83, lying 95 light years away. Its warm glow is the constellation's most distinctive feature. Next, we have Beta Leonis. Beta Leonis Minoris. I've got to remember that. A binary star system and second brightest star at magnitude 4.1. Located 254 light years distance. Two stars orbit each other in a gravitational embrace. And then we got 21 Leonis Minoris, a rapidly rotating white main sequence star, magnitude 4.5 and just 92 light years away. One of the fastest spinning stars visible to amateur observers. Okay, any exoplanets? Neo Minor is home to at least 3 stars with confirmed exoplanets, bringing the modern astronomical significance to this ancient-looking patch of sky. For instance, HD 87883 has a known planetary companion studied for its similarities to the outer solar system dynamics. And Kelt 3, a hot Jupiter system discovered by the Kilo Degree Extremely Little Telescope survey, a world of extreme temperatures orbiting very close to its host star. Deep Sky Wonders, very nice picture here of ARP or ARP 107, a pair of interacting galaxies caught in a gravitational dance, accessible with large amateur telescopes, a beautiful example of cosmic collision in a slow motion. It's a very nice image there from the Hubble, I believe, that one. And also another one known as Hanny's Vorwerp.
Oh, Hanny's Vorwerp, yeah.
So perhaps Leo Minor's most remarkable object, a rare quasar ionization echo near galaxy IC. Whoops. Sorry about that. A rare quasar ionization echo near galaxy IC 2497, the galaxy at the top, glowing an eerie green. Looks like a frog.
Yeah, it does.
Famously discovered not by a professional but by a Dutch school teacher through the Galaxy Zoo Citizen Science Project in 2007.
You see, viewers, if you join the Zooniverse, universe.org, and sign up to Galaxy Zoo to classify galaxies, you too can make discoveries like Hanny did, and earn your moment of fame. There you are.
That's it. Okay, folklore and mythology. Because Leo Minor was only formalized in the 17th century, it carries no Greek or Roman mythology. Classical poets and astronomers simply never gave this star field a story. Arabic traditions. In Arabic astronomical tradition, this region was sometimes evoked as the lioness or the gazelle with her young, poetic images drawn from the natural world of the Arabian Peninsula. The constellations story is ultimately one of scientific naming rather than mythological imagination, a reflection of the Enlightenment area drive to chart every corner of the sky. So thank you to Various for making this area of the sky known. And that's it. Thank you very much.
Thank you, Michael. Very, very nice. Another tiny constellation from Michael there.
Do you expect anything else?
No, we don't. At this juncture, Michael, we do not expect anything.
Occasionally.
There we are. Rogers tend to be much larger.
Yes.
And the constellations.
Yeah, and the constellations. Yeah. So we will be back to, we will be back to normal-sized, proper constellations.
Oh.
Yeah. So there we are.
Absolutely.
All right. All right, viewers, it's time for us to say goodbye for the evening. Thank you so much for being here. We've really enjoyed having your company tonight, and we hope you've enjoyed it too, and maybe learned a few things at the same time. Thanks for your donations and contributions, as ever. We will be back next week. Not quite sure with what yet, but we'll figure something out, as we always do. So from all of us at Space Oddities, we hope you have a fantastic week. Stay safe, take care of each other in these troubled times, and we will see you 8 p.m. UK, as always, on Space Oddities next week. So from all of us, goodbye.
Take care.